think I'd probably shoot myself in the head.
What?
Wow.
What a range of
There's no
responses.
That's so serious. Yeah.
Welcome to Walkabout the Galaxy, the Full House astronomy podcast, where the science is universal, the opinions are personal, and the recording day has changed.
Yeah.
Mm-hmm.
Oh.
We are Strange Charm, top and down, the Astroquarks, also known as Josh Caldwell,
Addie Dove.
Jim Cooney.
And Audrey Martin.
coming to you from the chilly Walkabout studio at the University of Central Florida. Remember to subscribe to us on all platforms, including YouTube, Facebook, Twitter, and Instagram, but not Jangletown, Pyramid, or Ragnarok.
Are those real social
sound
networks?
Probably
dirty.
not.
Jangletown.
Jangletown.
Yeah.
We got to get on that. You can
No,
contact us anytime at wtg@ucf.edu with questions, compliments. I'm going to be giggling about Jangletown.
It's your fault.
With questions, compliments, and questions about how to get a cool Walkabout t-shirt. Two kinds of questions: general questions or questions about how to get a Walkabout t-shirt.
Those are different.
Our stumper today is I'm now moved away from like comets or asteroids to what do you all think about this weird conundrum?
Okay.
Mm-hmm.
This conundrum, we've talked a few times on previous episodes about this idea that the universe is a simulation.
Mm-hmm.
And it's like one of those things that sounds like a joke, but then serious people like say it actually, is a thing that is hypothetically possible.
Yeah.
What if we found out that it was a simulation? How would you feel about that?
How does the simulation want me to feel?
You tell me.
Wow.
You tell me.
I think I wouldn't feel great,
I think I don't.
but also maybe it doesn't matter.
Yeah, I think I don't care.
It's kind of interesting
Would-
because you're not going to change anything about your life, right? There's like not anything you can do about it.
Exactly.
Can't hit Control-C
I'm no
Mhm.
or
Neo.
whatever. Huh?
I'm no Neo. I can't break out of the Matrix.
Right.
Yeah.
Yeah.
As much as I want to be Neo,
Yeah.
just upload karate
Go
to
around
my
taking,
brain.
taking blue pills as
Yeah.
much as you
Yeah.
can.
If I could upload information like that to my brain, I would be very excited about the prospect that this is all a simulation.
Yeah.
If not, it doesn't affect me at all, so I don't
Okay.
care.
So if you found out it was a simulation, you'd be like, oh, can I like download the booster pack?
Mhm.
Yeah.
And
Yeah.
then it would be like awesome that it's a simulation, but since you can't, you're just like,
No.
well,
Yep.
It is what it is.
Yep.
that's what it is. It's a
Just
simulation.
another one of those things we can't control.
I think I'd probably shoot myself in the head.
What?
Wow.
What a range of
There's no
responses.
That's so serious. Yeah. It doesn't matter in
Just
any way.
pure
Yeah.
apathy.
Whether it's,
Well, it gets to the whole point of what does matter at all in any
nothing.
way.
Nothing.
Well, if you're
But
already
everything
there,
you feel in
then,
a
yeah.
simulation is already in the simulation, then everything you will feel and everything you have felt is in the simulation. And so you
Yeah.
might as well stick it out until the simulation decides you shouldn't anymore.
Yeah. This is
And,
maybe
like,
a
how
little too deep
controlled-
for a Walkabout
How
episode.
controlled is a simulation? Also, is it just like a...
I don't know.
Okay.
You're living in it.
Well,
Not controlled at all.
yeah.
The bummer about a simulation is like at first it seems like it's like some explanation for why the universe is, but it doesn't.
It doesn't.
It's just another layer of onion or whatever. So
Right.
then you have to ask who wrote the simulation? Where'd they come from? How
What
did
are
they
they
exist?
doing?
Why
Who
do they
watches the
exist? That kind
watchers?
of things.
Yeah. That's a Star Trek Next Generation episode title. That I visited the set the day of they were filming that
Really?
episode. Yep.
You met
What?
so many people.
Did you meet
I
Sir Patrick Stewart,
I did not. No.
aka P. Stew?
No, but I
Please
did
do.
eat in the Paramount commissary at the neighboring table to Jonathan Frakes.
Wow.
Oh.
Yep, that's who I am.
Just speaking of Star Trek and eating,
Was once near a famous person.
one of Riley's things she says now, she makes some combinations of sounds now that sometimes sounds like words, but a lot of times things like sock and maybe cat all sound like gawk,
Uh-huh.
which is not a delicious dish.
Oh, gosh.
Gawk.
Sorry, your Klingon pronunciation.
I know. Yeah. Well, hers
is better.
You really
Yeah.
gotta work on that. Yeah.
Okay. Well, today we'll talk about none of these things. Instead, we'll talk
Worms.
about the crummiest wormhole, meteorites, and the exoplanet radius gap. But first, this episode of Walkabout the Galaxy is brought to you by Planck stars. If singularities make your head hurt, let Planck stars bring you back from the infinite. With the ability to contain all the information that falls into a black hole, these stellar wonders are supported against collapse by the stiffness of reality itself. Thank Heisenberg for these paradoxical stellar beasts whose unproven existence depends on loop quantum gravity theory. If that's got your head spinning, jump into a black hole for a ride with a Planck star. Planck stars. Find what feels good.
Snuggies.
Match.com.
Match.com.
I like Snuggies.
Find what feels good.
Yeah.
That's what you're looking for on Match.com.
Oh, it's not Jangletown?
That's what I was going to say.
Jangle
Jangletown. For old guys.
I'll give you a hint. It has to do with the word plank, or a homonym for the word plank, which in this case, the
Clamp.
sponsor Planck is Planck, named after the person.
Napple.
Yeah. I was
You're
going
not
to say
gonna-
something like Peloton or something.
Well, something related to yoga,
Oh.
because there's a plank pose
Yeah.
in yoga. So it's yoga with Adrian.
Oh.
Not you,
Oh,
Adrian.
Not me.
Nope.
I do not have a yoga
I love
YouTube
yoga
channel.
with
That's
Adrian.
We've been
vastly-
sponsored by Planck Length, Planck Constant, and the Planck Epic. And now we are sponsored by the hypothesized Planck star. Are you familiar with Planck stars?
No.
No.
Jim? The supporting pressure is basically Heisenberg's uncertainty principle or something or other like that I don't understand how it actually works, but you can't get the things closer together because then you would know too much about where they are or something like that. But it has also something to do with loop quantum gravity theory. Familiar with that?
Roughly. I mean, it's like a...
It's a string variant.
Right. Well, it's kind of an alternate... Here's the fundamental way to mix all of the theories together. It's alternate from string theory.
Yeah. So in these, in the Planck star would be the singularity at the center of a black hole, and it would not be a singularity. It would have a finite size.
Right. In quantum physics, you run into all kind of trouble with infinitely dense things, and so
Yeah. So
you
this
need
is one way-
the real
this is-
nature of the
this is
universe in order to figure out what's going on
one
there.
way around it.
Yeah.
Space news.
Space news.
There's some news from. I gather NASA gives up.
Yeah, NASA gave up. Just kidding. They didn't. Don't let the headlines fool you. The Lucy spacecraft, when it launched, so going back in time slightly, when it launched in October 2021, it had to deploy 2 solar panels, and they're round and they like fan out.
Is this the one going to the Trojans?
Yes.
Okay.
Yeah.
Yep.
And when they're fully deployed,
Oh, yeah.
oh yeah. When they're fully deployed, it'll latch. So like it's
Supposed
like
to latch.
it's supposed to latch. So it unfurls in like a circle, like an accordion, and then when it's fully unfurled, it latches. One of them didn't latch,
Oh no.
which is really scary because the spacecraft is going really, really far away from the sun, so it needs like a lot of surface area for the the solar panels to absorb all the energy. Well, over the last however many months since discovering that it didn't latch, the Lucy team has been trying to get it to latch by cranking a lever,
Cajoling, I'm imagining compliments,
so many
promises
yeah.
of favors and negotiating.
Yes.
They've gone through all the various stages of shouting and then pleading, and
tricking.
none of those things worked.
None of it. Now, the quote-unquote giving up part is that it's not latched, but they're going to stop trying to latch it. So it's 90...
Kinda sounds like giving up.
Sure.
Can I say that, the first thing they do with these spacecraft, when they solar-powered spacecraft, first thing you do is deploy the solar panels.
Yeah.
Right? Deploy, because they launch with a battery that's got some charge, whatever, but then you got to get the solar panels out to have your power. So they did that early. You mentioned it was launched in October of 21.
Mm-hmm.
Within days, we knew that one of the things that one of the things had not fully deployed, but they said it's 95% deployed and that's enough power. So for the last over a year, I have not even been aware that NASA was trying to do anything more with it. So
It seemed like there would only be a limited number of things you could do.
try.
Like, type in the thing,
Right.
latch.
Right.
And it doesn't latch. What the hell are you
what
going to do?
else are you going to do? Exactly.
Yeah, they
Type
tried
it
to
again.
realize.
Latch.
They're like
Latch.
Were they really undoing it a little bit and then like trying to slam it back open? Because I would never tell it
No.
Mm-mm.
No,
So
no,
what were
they
they doing?
So it's, if you imagine like a fishing reel, like
Can you
you're
imagine
reeling
that,
in.
Jim?
I can imagine a fishing reel.
You got it. So fishing reel.
He fishes.
Oh, that's why you can imagine it. So if the string comes off the spool, then there's only so many things that you can do, and that's what they think happened. That the string, the rope that was pulling in the solar panel came off the reel. So what they did was they kept trying to spool it in off of the reel.
And so they decided 350 times was the right number of times to try that or something?
They got to, so it's 98% closed, but they can't, it's not
That's
close
good.
enough
Oh, they actually
for it
got
to...
a little more than
Yeah, they
Maybe
did.
so,
So
okay.
it doesn't, it's not latched, but the tension is enough so that the solar panel is in place. What they were worried about is that, like, during acceleration or deceleration, it would flop around
I see.
and then cause the spacecraft to move around in a way that was, like, uncontrolled.
I see.
And so since these are flyby, since the mission is to fly by asteroids, it's going to do some maneuvering around
Right.
the asteroid, so they need it to be pretty stable. So they're good with it where it's
where
at.
it is.
And
Okay.
yeah, so if you consider giving up being successful, then NASA gave up.
Good job, NASA.
Yeah.
Yeah, it said, and it did a close flyby of Earth in October of 22, and it even was sort of in a little bit of Earth's atmosphere, it was close enough, and it performed okay.
Mm-hmm.
So that's a pretty good test of how well it's structurally going to hold up.
Yeah.
Just
Cool.
gotta watch out for those micrometeorites.
Speaking of meteorites, you like meteorites, right, Audrey?
Oh boy, do I.
Yeah. Well, nobody's perfect.
Ouch.
So there was
Weird
some
thing.
news about a big meteorite
Yeah.
from Antarctica.
Yeah, so scientists, they found a 17-pound meteorite in Antarctica.
Seems big. Is
It's
that big?
huge.
Also,
it's massive.
that seems tiny to me.
That's
Really?
It's
Like,
well, I don't know. I mean, so
rocks
17
are heavy.
pounds, I
But
can
most
pick
of
up
the
a
rocks we
17.
find are this big.
They're itty
Right?
bitty.
Really?
Yeah.
Yeah.
No.
Meteorites? Yeah.
Mhm.
Have you
It's-
been to the
we've-
Smithsonian?
Yeah.
Yeah, there are.
They
some
have
ton
multi-ton
meteorites.
meteorites.
Yeah, this one's
If you told me
17 pounds.
you found a 17-ton meteorite, Audrey, I'd say, hot damn.
Well, I
pretty
didn't find any meteorite, unfortunately. Although it would be really fun to go meteorite hunting. But yeah,
In
they found
Antarctica?
Antarctica. It would be
we
so
should
much
go.
fun.
Okay.
Yeah, so to go meteorite hunting, Antarctica is a really great place to do it because the ground is mostly white because of all of the ice, and so you can see these dark rocks against the ice pretty easily. And yeah, they found a friggin' huge one.
So
It's
a
big,
typical.
Partly because a lot of the ones they find in Antarctica too are ones that have been in glaciers and
Yeah,
they're getting
yeah.
revealed from glaciers over time. So you
Yeah,
find
that's
this
true,
till of meteorites left over.
Yeah,
But that's still pretty big.
I'll believe you. I just
There
I
are
was
bigger pieces.
I was messed up because a student of mine found a meteorite a few years back.
Really?
And it
Where?
was large. It was that large
No.
Yes.
Where? Who?
in Iowa.
No.
And it
When
was
he was
a
a-
real meteorite, or
It was a real meteorite. We had it 98% of the time when somebody comes in, a student comes in and says,
No.
"I found a meteorite." It's not a meteorite. It's,
Right.
it's some
It's more than 98%.
or
It's
more.
way
Yeah.
more than that.
But this kid brought it in, and I said, "You know what? That actually looks like a meteorite." I took it to our meteorite expert here at UCF, Dr. Dan Britt, and he confirmed that it almost certainly was a meteorite. We actually sliced a piece off, sent it out to a laboratory to have it analyzed and see and all this stuff. But in any event, it's a whopper. It was the biggest meteorite they found in Iowa. I think he was, this kid was like
Wow, that's cool. I didn't know
a
that.
farmhand, and he was digging a post hole and dug into a big giant meteor.
That's cool.
First time I've ever heard of a story like that, of
That's
someone
pretty great.
finding something in their
And it
backyard.
actually was.
It actually was a
Yeah.
meteorite,
Yeah.
and a big
Yep.
sucker. Yeah, but it was an iron meteorite, which makes it very. I don't know if this one was an iron meteorite. Or
I don't
a-
think so.
a
Most
stony meteorite.
Yeah, most meteorites that, at least that are found in Antarctica, or a lot of them are stony.
Yeah.
And it's easy to find them in Antarctica. But yeah, I
that
guess
would be fun to go. I agree.
Yeah, it would be so much fun.
Walkabout expedition.
Yes.
Yeah.
Antarctica.
Field trip.
Yeah, if you're listening to us from Antarctica,
Write us down.
if you're listening to us from Hawaii, I meant to say. And you mentioned tying it together, the Lucy mission, your interest in those two things goes together because it's the ancient leftovers from the formation of our solar system,
Exactly.
and very important things. I can't really handle meteorites because I have a mental block about mineralogy and geology and all those things. So I'm happy that you're on top of that, Audrey.
I got you
or
covered.
I should say down with that.
I'm down. Yeah.
But speaking of the origin of planets, there's a new study out about exoplanets.
Yeah.
And I think in a recent episode we talked about the distribution of the sizes of planets around other stars, not really looking very much like the distribution of planets around the sun. And in particular, there's a prominent hump at the size of about 50% larger than the Earth, or so, 50% to maybe twice as big as the Earth, called super-Earths, which we don't have any in our solar system. We got 4 times bigger with Uranus and Neptune, and 10 times bigger with Jupiter and Saturn, and the same size with Venus. But these super-Earths seem to be a very common sort of size of planet. As we talked about how those super-Earths come about. But it also turns out that there's a gap in the distribution of sizes between sort of Earth-sized and the super-Earths. There's not like this continuous distribution of like a little bit more as you get smaller, and then a little bit more and a little bit more. It's like it goes down and then it goes back up again. So,
And we have enough data at this point that it's pretty statistically significant.
yeah.
That's what I was going to ask. Is how many? I mean, we found a few thousand exoplanets,
Over
or
5,000.
confirmed,
Yeah.
but most of the early ones were not Earth at all things. They were huge,
Right.
giant things. But I guess
Right.
nowadays with Kepler and so forth, we found enough
Yes.
small ones that we do have statistical
Yes.
significance. Okay.
Yes.
Cool.
Yeah. And like there's actually we were reading, one of the sources we used for this was a Scientific American article that had a figure from a previous paper from 2018 where they like showed the survey results of sort of this radii, sort of the radii bins in which planets exist, and there's this radius gap, and they do say like below 1.2 Earth masses. They don't really include the data because there's just not enough data.
Right.
So there is this gap though, and I forget, it's a radius gap that's between like 1.4 times wider than the Earth and 2.4 times wider. We see more stuff that are super Earths, so about 1.4 times, and we see a bunch of stuffs that are mini Neptunes that are mini Neptunes at 2.4 times, but there's not a lot in between.
And so I guess
so one of the previous go ahead.
Yeah, go ahead.
One of the previous suggestions for how this happens is more like temperature driven. So like with these smaller ones, planets move closer in, and so they lose they're lighter, so they lose their gas, whereas the ones further out are sort of heavier and can hang on to their gas.
Yeah, this one, there are all sorts of gyrations that astronomers went to with the discovery of these thousands of exoplanets and how different those systems looked compared to our own system. And a key feature of those gyrations in our explanations was planetary migration.
Yeah.
So in those early days of planet formation, there is a disk of stuff around the star, and that disk interacts with the planets and causes them to move around. And so that's how we get hot Jupiters. And our old model was like, you can only make a big icy gassy planet like Jupiter far away from a star where it's cold. Then we started discovering a bunch in very close to a star, and it's like, they were made out there and then they moved in. And for the peculiarities of our solar system, Jupiter didn't move in. Or maybe some Jupiters did and they're gone. And we got that Jupiter out there. So yeah, the previous explanation for this radius gap
temperature driven
was related to planets moving in and then that size losing their atmosphere due to the increase in temperature.
And smaller in mass to hold on to it. But there's these other authors, Isidoro et al., who have this, they call it the breaking the chains scenario, which they've previously proposed, but this is an updated model. And it's breaking the chains because, and with a peas in a pod feature.
Oh, that's really cute.
So the breaking the chains has to do with the fact that they think that, so you have this disk. I should really teach this paper in my class this
You
semester. They have this, when you're forming planets, you have gas and dust, and after the gas is dispersed in the disk, they say that more than 90% of the planetary systems become dynamically unstable. So more than 90% of planetary systems then experience sort of this upheaval.
Things go nuts.
And it's more than just this like little migration. It can be like things just absolutely going nuts and like things
So that would
all
be
over the
like
place.
planets' orbits crossing each other.
Yeah, so like we think happened maybe potentially for some of our planets that caused like the late heavy bombardment on the moon, threw a bunch of stuff in the earlier in the solar system. But that's probably how we get things like hot Jupiters and stuff like that too. But so when this happens, it also creates a lot of impacts. And so the big crucial thing, which we also
love impacts.
we love some good impacts, and it's a
Love
really,
some-
it's
love-
always a good way to explain things too. It's just like, I don't know
Oh,
why,
yeah.
throw
Something
something
All
at
the
me.
Slammed
exceptions
into
to the
it.
rule.
Yeah,
Impacts.
exactly. Impacts. And so in this case then, these late impacts can strip primordial atmospheres of low mass planets because again, they don't have as much mass, so it's harder to hold on to the gas. Whereas the big planets don't get stripped as much because
Right.
they can sort of swallow up those impactors and keep their more of their atmospheres.
Impacts once again to the rescue,
Yeah, exactly.
explaining oddities. Yeah, I mean, we use big impacts in our own solar system story for the tilt of Uranus and the creation of Earth's moon and Mercury's absence of its very, very, very high density, sort of just along the same general lines where you're describing, strip off the outer part of it. Yeah,
Yeah,
leave
and
behind.
the peas in the pod feature is that
Yeah.
a lot of planets, many systems, where there are several planets around a given star, they'll have similar sizes to each other and regular orbital spacing. So we've talked a little bit about
Right.
that, where there's sort of like similar sized planets around a star,
Yeah.
and that's the peas in the pod. And so they actually see some of that in this model also.
Okay, so that ties in with this other story. It was a different paper and a different set of authors we were talking about before with the super Earths and why super Earths around
Yeah.
that particular planet sort of tend to be peas in a pod. We
Yeah.
were, I think, using the cookie cutter
We were,
analogy
but apparently
for
it's
that.
several peas in a
Several
pod,
peas in a pod.
which is kind of
Oh,
cute.
I
Okay.
like that more.
That's my favorite vegetable.
The peas?
Peas
They're not
From a
really.
pod.
directly in a pot. I mean, like eating them,
Oh.
going out, get the pot, open it up, eat them.
Isn't a
Okay.
pea a
If you
legume?
cook them, they're disgusting.
Okay,
Oh,
interesting.
Sorry.
the snow pea?
With zero
English pea.
With zero segue at all, our trivia today is telescopic.
Oh.
Okay.
We've been getting a lot of great stuff from JWST,
Mm-hmm.
and of course we're learning a lot about exoplanets, trying to make a segue from all these cool telescopes out there.
Uh-huh.
And I don't know if you ever have, like, show a non-astronomer stuff with a telescope. What is the one thing they want to know about that telescope?
How big is it?
No, they're looking at it. They see how big it is.
Oh.
So you got your friend over, you
Yeah.
have your telescope.
Can I
What's
take
the
a picture?
magnification?
What's the magnification?
I don't think they ever ask
No,
that.
no one
They
asks
do.
that.
They
No.
absolutely, that is all they want to know is what's the magnification of that telescope.
The undergrads don't care.
Well,
My friends don't care.
so that's the basis for your trivia this episode, and it's partly because the magnification isn't really what's important. It's a little
That's
bit
right.
important, but it's not really what's so important with telescopes. So the first question is, what was the magnification of Galileo's first telescope? What was the highest magnification telescope he made?
Oh.
Because he used more than one telescope over his observing career. And then for the Hubble Space Telescope, which is such an amazing telescope,
Indeed.
Still going.
we can't really talk about magnification because you don't put your eye up to it, right? And look through it. It takes pictures. So rather than magnification, we'll talk about the resolution that it can perceive, angular resolution compared to the human eye's angular resolution. So, you know, you can you can tell the human eye has a sort of pixel ratio that it can see depending on what a distance is. I'm not saying this very well, but you know what I mean? It's like at a certain point, if an image gets sharper, you can't tell the difference with your eye, right?
Right.
But the Hubble Space Telescope can, so we get some exquisite detail in things that are very, very far away. So the analogous to the magnification question for Hubble will be, how much better is its spatial resolution than the human eye? Okay?
Okay.
And same thing for JWST.
JW.
So moving out then into the grand world of cosmology with Hubble and JWST, Jim, do you have something you would like to talk about on today's episode?
You're allowed to talk
I
now.
think this is so. This is not cosmology at all, but it is.
Oh.
I know, and Josh has said all things that have to do with
if it's not-
black holes or relativity are cosmology.
Yeah.
That's right.
Mhm.
The universe can be divided into two things, planets
Planets?
and cosmology.
There you go. That's right. That's about right. This is something actually that Josh has been.
Tangletown.
Josh has been.
Jangle, jangle.
Josh has been wanting to talk about for a while, because this is a thing that involves black holes, wormholes,
Check.
quantum mechanics, and quantum computing.
Oh,
Which
man.
it's just like all of the big buzzwords for
Yeah.
modern physics fun.
Yes.
Funded.
Right.
And there were a bunch of articles out there in the somewhat popular media that sounded like the one we were looking at earlier today. It was physicists create the smallest, crummiest wormhole you can imagine. That's
Oh.
a little bit cheeky, but
So
still
rude.
overselling it. Still massively overselling it.
Yeah.
Because what it sounds like they've done is physicists
sounded
have
like
gone
it-
into a laboratory and made a wormhole.
It made a wormhole that was this big.
Yeah, maybe a tiny one, maybe not one you could use
And
to
maybe
get
it only
to...
lasted. Like you read that and you're like, okay, it was in a lab.
Yeah.
It was in a vacuum chamber, and so it's probably microscopic, and
Yep.
it probably only lasted for like a nanosecond.
And
or
it like
something
wasn't
like
of
that.
good quality. It was all
And
raggedy.
it was it was
Yeah. It was mean
Like-
to its friends. Yeah.
bouncing around or something. Yeah.
Yeah,
But it's not even that. It's not even that good.
It's not even that good.
What
No,
did
it's
they
not even that
do?
good. They just simulated on a computer.
What?
a wormhole.
That doesn't count.
Right.
I think I could do that.
Yeah.
Kind of.
They must have done something more than what a game designer does when they make, wormhole attack of the extraterrestrials through the wormholes.
I played that game.
Kind of, yeah. I mean, kind of not. Well, one of the cool things is they did
Kind
it
of,
on
kind
a
of not.
quantum computer.
Oh, yeah.
Which
Take that,
is-
Josh.
Yeah.
I can't do that.
Take that and make
yeah.
it on your quantum computer.
And I will, so quantum computers are like the cutting edge of
Computing.
and quantum information tech. I mean, it's all.
Yeah.
I don't
Are they
even know.
there or aren't they?
There are some quantum computers. I've seen pictures.
There are quantum computers.
You can buy them.
Do they tunnel through walls?
They don't,
No.
but the information does. I'll tell you what I think the
All right,
coolest
let's
part of all this
focus.
is. So focus. What they're trying to do is kind of explore a territory that is the connection between gravity, which is described by general relativity, and quantum physics. Right? That's the holy grail of physics. Right? It's combine those two things into some kind of theory of quantum gravity. That's what the quantum loop gravity that you mentioned earlier is trying to do. That's what string theory is trying to do.
Because on the surface, they don't go well together.
They do not go well together.
Quantum general relativity is all beautifully smooth and continuous,
Right.
and quantum is not so much.
Yeah, it's all discrete when you look really close. So they don't mix. And so it turns out, though, that you can kind of get them to play together in kind of analogy form. And one way they do this is this thing called the holographic principle. So the idea is if you have just quantum mechanics, you can... So say you're playing in 3 dimensions in quantum mechanics. It turns out that that's totally analogous to having quantum mechanics plus gravity in 4 dimensions. Now what the hell does that even mean?
Wait
I
a
don't
minute.
know.
Say
What?
that again. If
Yeah.
you have
This is like our I don't know.
quantum mechanics in 3 dimensions, don't we have
So-
quantum
so-
mechanics
so-
in
so-
3 dimensions?
I don't.
We do.
Oh.
We do.
Okay.
But maybe we don't really live in a 3-dimensional universe. Maybe we live in a 4-dimensional universe, And weird gravitational effects in this fourth dimension are causing the weird quantum effects in the third dimension. I'll give a more
good
concrete
analogy.
example.
Can you
More
turn this
concrete.
into something with like a balloon or a rubber sheet and a bowling ball or something?
Or maybe a loaf of bread.
Well, it's
raisin bread.
Raisin.
or
it's
something?
much like so the idea is if you it's like with a hologram, right? In a hologram, you make this three-dimensional thing,
Okay,
but all of the information is encoded on a two-dimensional surface.
sure.
Oh.
And so the idea is maybe we live in this, maybe we live on the surface of a higher dimensional thing.
We're in a simulation.
We're a three-dimensional
A little bit.
hologram of a fourth
dimension, something like this.
Something.
So let me
Oh.
let me explain why this is such a cool idea. So one of the in 1935, Einstein. Back in 1935, Josh remembers this. You were around.
Oh, where's Tracy when you need her?
1935. We weren't around in 1935. Einstein, along with some co-authors, wrote two different papers on two totally different weird things. One was about wormholes. That is, like how you could conceivably, in general relativity, connect two ends of two black holes. Right, black holes you like fall into, you can't get out of. But turns out, you mathematically, you could mush them together so that they're, you know, they connect. You go into one, you kind of come out the other. You can't get out the other side because it's a black hole, but you can kind of get into the other black hole, into the interior of this other black hole.
Can I run something by you? Tell me if my simple-minded understanding is remotely correct. The equations of general relativity basically are geometry equations.
Yes.
That describe the shape of what space.
Yeah.
And so the black hole shape is this sort of very, very pointy, deep hole.
Yeah.
So then if you can imagine another pointy, deep hole connecting to that, that's the wormhole. So your equations have a solution where you can have those two things connected.
Right. And the mouths of those things, the actual black holes themselves, can be pretty widely separated in space, but the distance that you would have to travel to get from one black hole to the other black hole through the black hole could be very short.
Right. So that's the worm.
That's the worm. That's what a wormhole
Wait
is,
a
right?
minute. Okay, this is totally flipping what I thought a wormhole was.
You thought it had to do with apples?
I thought, yeah, it was an apple with a worm in the center. No, I
Gross.
thought a wormhole was like you go in one side, you come out the other. But if it is two black holes,
The other side
then
is,
you can't
is
get out.
another black hole.
Yeah, so you
Right.
can't get out. So
You
it's
can't get
not
out.
like
So you're right. Well, you can't get out unless you have some crazy kind of
Other
matter.
physics.
You need some negative energy matter.
I have a
in
lot
order
of
to
negative
get-
energy.
You do.
Should I
You do
channel that?
sometimes, yes.
Okay.
So anyway, yeah,
So
I mean that's the whole
alright.
thing. Is it's this theoretical thing, but it's useless because you
It's-
can't
it's-
actually traverse it. It's not a
It's
not a traversable
It's a
thing.
solution to this complicated general
Yeah.
equation that says there is a solution that basically has a tube
Yeah,
that connects two different, very, very distant parts of the universe
That's right.
together.
That's right.
But at each end of those tubes, you're in a black hole.
You're in a black hole. But again, you can make this traversable with some non-physical kind of things. This negative energy stuff.
Okay.
But you know where negative
So-
energy does actually exist?
In black
Besides
holes.
Addy?
In quantum physics.
Well,
In quantum physics, you can do really weird things. You can steal energy. You can get negative
that's right.
energy, right?
That's right.
Right.
All kind of weird things. In fact, in that same year that Einstein was writing about, in Friends, and Rosen was writing about these wormholes, he was
They make
upset
bridges.
at that time about quantum physics, right? Because
Right.
quantum physics is super weird, and of course, he was famously upset about what we now call quantum entanglement, right?
Yeah.
Where you have
Two particles. that-
which are related to one another. You don't know what the state of either one is, but as soon as you measure the state of one, the state of the other one is determined.
Right.
And sometimes those two particles separate. They could be light years apart. When you measure the state of one, that immediately means the state of the other one, which was ambiguous before, is now
No.
non-ambiguous.
Right. Even though it's light years away.
It's light years away,
You
so it's
instantly know.
You instantly know what its state is, right? And Einstein called that spooky action at a distance. He didn't like it, and he was using it as an example of how quantum mechanics can't be right because. But it turns out it is right. Then we use entanglement in our labs in physics nowadays a lot. Turned out that it could be that quantum entanglement, is just an example of traversing a wormhole in this higher dimensional space.
Tiny wormholes?
So that's the
So that
kind of
is
wormhole?
the kind of the idea is that general relativity and quantum physics, their equations might be saying the same thing if you're looking at them in different dimensions. So there might be two.
Aw, so they get along.
They might.
Really good.
They might. And so what this recent thing was they were writing a computer code on quantum computers to kind of simulate this happening. So they did not in any way, shape, or form produce a physical wormhole in any way. So there was not.
That's
But we'd never
disappointing.
even been able to do it in a computer before.
Yeah, is
Right.
the quantum computing part of this important?
Is
It
that
is.
an essential
It is.
element?
Why?
Well, it is and it is not. So
Make up your mind, Quantum.
I don't think he
Wow.
can.
Just like-
so
All
so
his answers are
actually,
going to be yes and no.
the short
It's
answer
an addition.
the short answer is actually no. So
Quantum
that is
gym.
the size of the quantum computer that they used here was such that you could, with a large enough conventional computer, reproduce these results with that.
Okay.
But
Once we
They
get
thought
better
it-
quantum
it's more like a
computers-
proof of concept that they were able to do this with this quantum computer. If we run a test, and this was really a test of a really baby simple one of these holographic
tiny
principles.
little crummy wormhole.
If you wanted to do it in a more realistic quantum gravity type of thing, you'd need a much larger
Quantum
computer, and it would be impossible to do that with a conventional computer.
Oh,
And
because of like
so-
the parallel processing.
Because quantum computers with only a handful of
Qubits.
their version of a bit. This was a 9-qubit computer that they were using.
It's insignificant.
Is enormously powerful just because
Yeah, that's mind blowing.
it is unbelievable. So
We should have somebody
And if-
on to explain
and we
to us
have-
what quantum computers are sometime.
yeah,
Oh,
We have,
I-
we have a
we know-
quantum. We have
I
it here at
know,
UCF.
I
We
know.
should. I was
used
thinking
to
about that
do
very same
quantum
thing.
computing research in undergrad.
What?
Maybe we
All
can
right.
have Audrey on someday.
Yeah,
to
Audrey.
talk
But
about
I was
quantum
an undergrad
computing.
and I don't remember
Okay.
most of it.
All right. Well, we can have our ex
We'll have
person
our
in your
expert.
job, which
Yeah.
Edward, which you'll know he can tell us all about that.
X
So
person
anyway,
in your
this
job.
is
Very odd turn of phrase.
Thanks, Quantum Jim.
yeah. So anyway, I
Okay,
don't claim to understand much of this, especially the
You
quantum
did a
computing
lot of
part.
talking about it,
Yeah.
so
I
good
did.
job.
I did, but I like it just because it's at least in theory a connection between
So,
a way of
if I may try to recap,
yeah, go for it.
they used a quantum computer
Yep.
to create or to simulate a solution to general relativity and quantum mechanics that involves a projection of a higher dimensional thing into our space that produces a wormhole solution.
Almost not actually in our space. They were doing it in a dimension lower, but
Okay.
yeah,
Okay.
they were doing this and it worked.
Also,
Like
Yeah.
they put information into one side of the simulated wormhole / thing, and they got information back out the other side.
and to tie
Okay.
to
Star Trek, here we come.
one of the things we were talking about earlier, the sort of hypothetical length of this wormhole is 3 Planck lengths.
Oh.
Yeah, really tiny.
3
Ooh.
Planck
3
lengths
Planck
long,
lengths.
where
That
Planck
is
length
tiny.
is 10
As
to
a
the
baby.
negative 33 centimeters.
Yeah, which is in quantum mechanics typically thought of as the smallest possible length.
Yes.
There can be no
Right.
lengths smaller than that.
It's like the absolute zero of
Oh.
temperature.
Right. So it's only 3 times that. Pretty tiny,
That
pretty crappy,
is-
pretty crummy, and
that is-
it's only simulated. So-
Yeah.
That is
Yeah.
the smallest, crummiest wormhole ever. Well, let's talk about the smallest, crummiest telescope ever. Galileo's
Oh.
first telescope.
But
Wow.
man,
Ouch.
did he rock
Did
the
it?
house with it though?
He did.
Yeah.
So, what was the magnification on Galileo's first telescope?
40.
She sounds very confident,
Mm-hmm.
so she probably knows that. I'll go with 3. 3x.
10.
Jim has it on the number.
3?
Whoa.
Yes.
What?
Wow.
Yeah.
What?
What was
Okay.
the highest magnification telescope he made? Now knowing what his first one was,
80.
5.
10.
I'm giving it to Audrey.
Yay!
It was 30.
Oh, I should have
All right.
stuck with my first
Nice.
answer.
Yeah,
Yes.
yeah. All right, so now
For some reason, I was thinking, okay,
yeah.
well, obviously I was wrong.
What is the ratio of resolution of the Hubble Space Telescope to the human eye? In other words, how much finer a thing? So, Hubble takes these images. There's only, at a certain point you're just making pixels bigger. You're not actually going to be able to see any finer detail of what it's taking
Right.
a
If you
look
take
at.
if you take a
In-
little image and blow it up without increasing the resolution, you just made a big fuzzy image,
Right.
which doesn't help you.
But it has a higher spatial resolution than our eyes.
Mhm.
How much better? How many times better is what I'm looking for.
400.
240.
2,000.
I'm giving this to Audrey also.
No.
1,200.
Oh.
1,200.
Wow.
1,200.
Good job,
It's
Hubble.
kind of
Yay.
logarithmically, it's Audrey, arithmetically, it's Jim, or maybe you guys were tied.
I'll take it.
Yeah.
Yeah.
JWST, do you think resolution-wise better or worse than Hubble?
It's in a different wavelength.
It is a different wavelength.
Mhm.
So that's
That's
makes
key.
it hard. Yeah.
It's bigger telescope,
It's a
but
lot
a
bigger.
longer wavelength.
Longer wavelength.
It's also not at one wavelength.
No,
Nor is
yeah,
Hubble.
yeah.
I think it's better by a factor of 2.
Oh yeah, we're giving a number.
Sure. Although I don't know, I don't know the particular wavelength that I have this answer
Mm.
at. So
Better by a factor of going with 10. 10.
Lower by a factor of 2.
Addie gets it.
No,
All right.
lower.
Yep. The
What up?
this telescope is bigger, but the wavelength is much bigger,
Yeah.
and the longer
Mm.
wavelength kills your resolution. The bigger
Still
mirror
makes some pretty awesome
helps your
images.
resolution.
Well, poop.
My mom
Doesn't
used to
take
always
away
ask
from
me
them.
when we'd see these amazing
Does.
pictures in space, that are like shown these are in true color or whatever, because Hubble's got detectors in the visible part of the spectrum. It's like, is that really the color? Is that really what it would look like? It's like, those are the colors, but that's not what it would look like because they're so faint. These like beautiful pillars of creation and all of that
Mhm.
stuff are just, it's not a matter of like being there or anything. You could go there, you wouldn't really see it
Right.
because it's just too faint.
Yeah.
So the real thing with the telescope is not the magnification, it's the light sensitivity. It's the ability to accumulate all of that stuff. So, that's the real.
Yeah, two things: resolution and light collecting ability are
Yeah.
the two things which. And luckily enough, in general, making a telescope bigger makes both of those things better.
Yep.
Yeah.
Well, while it may have felt like falling into a wormhole, it was just another episode of Walkabout the Galaxy. Give us 5 stars and we'll give you the universe. Be sure to follow us on Facebook and Instagram to get all our updates, and check out our website at walkaboutthegalaxy.com. Subscribe to our YouTube channel and catch up on old episodes wherever you get your podcasts. Follow us on
At walk_the_galaxy.
and ask us questions at WTG@UCF.edu. Our theme music was composed by Richard Jerusik. Production assistance is provided by Logan Basinger. Thanks to our listeners in Los Angeles County and around the world. Stay safe. I'm Josh Caldwell.
I'm Hattie Dove.
I'm Jim Cooney.
And I'm Audrey Martin.
We're the Astrocork signing off until the next episode of Walkabout the Galaxy.
Jangletown.
Knew that was coming.
Jangletown.
Yeah, it's
All
like a meeting thing for old senior men.
Oh.
Jangletown. Really?
Oh.
Yeah, that's right. Good visual.
God.